Unit 1, Vector Algebra 1. What is the velocity of the bird with respect to ground? Solve TQ3A to find an answer. Comment this. Structure. Introduction. Expected learning outcomes. Scalars and vectors. Scalars. Vectors. Equality of vectors. Unit vectors and null vector. Vector algebra. Addition of vectors. Subtraction of vectors. Product of vectors, scalar product, vector product, summary, terminal questions, solution and answer. Study guide. We hope that you have studied physics and mathematics at the senior secondary plus 2 level. We shall take it for granted that you know the basic concept of vector algebra presented in this unit. Therefore, we shall quickly revise those concepts in this unit. You have to make sure that you know this concept about vectors very well and then study the remaining course. We have given a set of problems as pretest in the beginning of these units and an FAQ in each section of the unit. Each of these should take you at most 5 to 10 minutes to solve. If you are able to solve them, then you know this basic vector concept. You can skip studying this section. Otherwise, you should study the sections thoroughly and make sure you can solve the problem before studying the next unit. Of course, you should try to solve the problems on your own without first looking at the solutions and answers. Don't worry about your difficulties in mathematics. I can assure you mine are still greater. Albert Einstein. Introduction. In your school physics, you have studied about many physical quantities and have learned to classify them as scalars and vectors. For example, you know that mass, temperature, and time are scalar. You also know that velocity, momentum, acceleration, electric field, etc. are vectors. You must understand the vectors are mathematical concepts used to describe the real physical properties of the world we live in. Vectors as we use them today were developed mainly in the 19th and 20th century. Though they have a longer history in a slightly different form. You may like to read the history of vector at this site. At the beginning of this unit, we shall revise the elementary concept of vector algebra. In section, you will revise how to classify physical quantities as scalars and vectors. You will also revisit the way of representing vector quantities geometrically without any reference to the system of coordinates. In section, you will solve problems on how to add, subtract, or multiply vectors with scalars using this representation. You will revise the concept of scalar and vector products of vectors in section and represent various physical quantities as product of vectors. In section, you will also solve problem applying the concept of presented there. In the next unit, you will revise the algebraic representations of vectors. Expected learning outcomes. After studying this unit, you should be able to classify physical quantities as scalars and vectors, express a vector in its geometric representations, define unit vectors, determine the component of a vector in any direction, add and subtract vectors using the geometric representation, compute the scalar and vector products of two vectors, and solve simple physics problem based on the application of vector algebra using the geometric representation. Don't forget, In your written work, always use an arrow above the letter you use to denote a vector. Example, R arrow. Use a cap above the letter you use to denote a unit vector. Example, R cap. Scalars and vectors. Do you recall the definition of scalars and vectors? If so, use those definitions to classify some physical quantities as scalar and vectors in the pretest given below. Otherwise, revise this definition given in section and, and then try to solve this problem again. Pretest. Test what you know. Comment this. If you have solved this problem correctly, you know how to classify physical quantities as scalars and vectors and represent vectors geometrically. You can skip section and otherwise study them and try the pretest again. Scalars. In your school science courses, you have studied about many physical quantities like mass, length, charge, temperature. These quantities are described by a number followed by an appropriate unit of measurement. You know that such quantities are called scalars. Let us first revise the definition of scalars and state some of their properties. Scalars. Physical quantities that are scalars are quantities that can be completely described by a number followed by an appropriate unit of measurement. We represent a scalar in a diagram or an equation by a letter or a symbol which represent both the unit of measurement and the number of units for the particular scalar quantity. For example, we can represent the mass of an object by the letter m, where m would be a number with a unit. Example, 60 kg. Similarly, the temperature at the core of the earth is T, where T equal to 300 degrees Celsius. Scalar quantities are added, subtracted, multiplied, and divided exactly like ordinary numbers. In fact, all the rules of elementary arithmetic operations apply to the values of a scalar quantity. Thus, if A, B, and C are three values of the scalar quantity, for example, the mass of an object, then these satisfy the following properties. A plus B is equal to B plus A. AB equal to BA. A plus 0 equal to A. A into 1 equal to 1 into A. A into B of into C. AB of C. A of B plus C equal to AB plus AC. Scalar quantity have another important property. A scalar is a quantity whose values does not depend on a coordinate system. It remains that same in all coordinate systems. This property is called invariance. Don't forget, scalar quantities remain invariant, unchanged under any transformation of coordinate system. Vectors. In your school physics, you have also studied about many physical quantities that are vectors. For example, the displacement, velocity, acceleration of object, the force being exerted on an object, and the electric field of a charge and vector quantities. We revisit the definition of vectors and the way we represent them geometrically. Vectors and their representations. Physical quantities that are vectors are quantities that can be completely described by a magnitude, which is non-negative scalar quantity. That is a positive number along with an appropriate unit and a direction in space. However, if the dimension of the vector quantity is a pure number, then we do not specify a unit. Example, in the case of unit vectors, geometric or graphical representation of vectors. Note, to specify the direction of a vector, we need to specify two characteristics, namely the orientations And the sense of the vector quantity, the orientation of the vector, is the relationship between the vector and any reference line or plane in space. The sense of the vector is determined by the order of 2 points on a line parallel to the vector. It is represented by the arrowhead. To represent a vector geometrically or graphically, we need to specify both its magnitude and its direction. So a vector is represented by a directed line segment or an arrow, that is a straight line with an arrowhead. The length of the arrow represents the magnitude of the vector quantity, which is a positive scalar quantity, and the arrowhead points along the direction of the vector. The arrowhead is placed either at the end or somewhere along the line segment. See figure. In figure A, the point A is called the tail, the starting point of the vector, and the point B is called the head, terminal point of the vector. The direction of the vector is from A to B. The line along which the vector is directed is called the line of action of the vector. In figure, this is the line AB. It is at an angle theta with respect to the reference line, which is the plus x-axis in this case. Geometric representation of a vector. A vector is a directed line segment having both magnitude and direction. Tail A, head B. B, the angle theta specifies the direction of the vectors. B, theta A B plus x. We usually denote a vector in a diagram or an equation by a letter or a symbol with an arrow on top. In the printed text, we will denote vectors by bold-faced letter with an arrow on top. Example: A vector, B vector, C vector, etc. In your written work, you should denote vector by drawing arrows above the letter denoting them. Example: A vector, B vector, C vector, etc. In print, we will denote the magnitude of a vector by a vector mod, called the modulus of a vector, or by a light letter in italics. You may now like to go back to the pretest problem and work them out to test your understanding. In the next section, we briefly revise some concepts about vectors, which you have learned in your school, namely the equality of vectors, unit vectors, and null vectors. If you know this concept well, you should first try to solve SAQ1. Skip the discussion in section if your answer is correctly. Equality of vectors, unit vectors, and null vectors. We explain each of these concepts in boxes, give some examples, then you can try SAQ1. Equality of vectors. All vectors shown here are equal. Equality of vectors. Two vectors are said to be equal if they have the same magnitude and the same direction. We denote the equality of two vectors A and B by writing a vector equal to B vector. For example, the four vectors shown in figure are equal even though they are drawn at different places on the pages. This is because their magnitudes are equal and they are all in the same direction. Remember that the locations and starting points of equal vectors do not matter, but they should be parallel to each other and represent the same quantity. Such vectors are also called free vectors. By definition, a free vector remains the same when translated parallel to itself in space. In physics, sometimes the line of actions of vector remains fixed. For example, the line of action of the acceleration due to gravity, g vector, of a falling body is fixed. Similarly, a force exerted on a rigid body may be applied at any point on the body on its line of action. In such cases, two vectors are equal only if they have the same magnitude and direction and the same line of action. Such vectors are often called sliding vectors. Unlike free vectors, which can be translated parallel to itself anywhere in space, a sliding vector can be translated only along its line of action. Sometimes even the initial point of a vector is fixed. For example, the initial point of the force applied on an elastic body or the point of application of the force is fixed. The deformation caused by the force F vector applied at some point A on an elastic body is different from the deformation caused when the same force is applied to a different point B on the body. Thus, the effect of the force depends on the points of application. Such a vector then has a fixed magnitude, direction, and point of application and is called a bound vector. In this case, two vectors are equal only if they are identical. If a vector A has the same magnitude as any other vector B but is in the opposite direction to B vector, then we have A vector equal to minus B vector. We now define a unit vector. Unit vector, a vector of length or magnitude 1 is called a unit vector. By convention, the unit vectors are taken to be dimensionless. A unit vector is used to denote a direction in space. A vector can be represented as the product of its magnitude A and a unit vector along its direction denoted by A cap. Then we write a vector equal to A into A cap, or A cap equal to A vector by A equal to A vector by mod of A vector. A unit vector A cap in the direction of a vector A, its magnitude is 1. We pronounce A cap as A cap or A hat. A cap A vector. Don't forget, a unit vector specifies a direction. Once we define the unit vector in a given direction, we can express any vector in the direction as the product of its magnitude with this unit vector. A unit vector does not have a dimension or a unit. Using a unit vector, we can write d vector 5m I cap and d vector equal to 10m I cap. Let us explain why we need this concept. Suppose a person P travels 5 meters eastward and another person Q travels 10 meters in the same direction from the some point O. The figure, we can define a unit vector having magnitude 1m point towards the eastern direction and denote it by I cap. Then with respect to O, the displacement of P vector, D vector and Q vector, vector D are given as D vector equal to 5m I cap and D vector to 10m I cap. Now to represent any new vector in that direction, we only need to multiply its magnitude by I cap. Let us now define the null vector or the zero vector. Null vector or zero vector. A null vector or zero vector is a vector which has zero magnitude and no definition direction. It is denoted by the symbol zero cap. Zero vector. Why do we need to define a null vector? Consider this example from physics. Suppose a girl walks 1 kilometer due north and then turns around the walks 1 kilometer due south to return to the starting point. What is her displacement? Its magnitude is 0, but since displacement is a vector, it has to be represented as 1. We say that the girl's displacement is 0 vector. Similarly, when two equal and opposite forces are exerted on a body, the net force on it is the zero vector. Zero vector. When we multiply a vector by a scalar m equal to 0, the result is 0 or null vector 0. You may now like to attempt an SAQ, try SAQ 1. SQ equality of vectors, unit vectors and zero vectors. Diagram of SQ 1C. Comment this. So far, you have revised the definition of vectors and their geometric representation. You have also revised the concept of equal vectors, unit vectors, and zero vectors or null vectors. You know that in physics, while expressing physical quantities and laws mathematically, we need to perform mathematical operations on vectors. These operations follow specific rules different from those for mathematical operations on scalars. In section 1.3, you will learn some elementary mathematical operations on vectors such as vector additions, subtraction, and multiplication of a vector by a scalar. Vector algebra. Vector may be added and subtracted as well as multiplied by a regular number scalar in section, and you will revise addition and subtraction of vectors using the geometric representation of vectors. If you can solve the SQs 2 and 3 in this section, then you know this concept and you can skip this discussion. Otherwise, solve them after studying section 1.3.1 and 1.3.2. Addition of vectors. Suppose two forces act on an object and we wish to find the net force on it. We can find it by performing the operation of vector addition. In this operation, we add two vectors quantities, say A vector and B vector, which are of the same type. For example, two displacement or two forces to produce another vector C of the same type. We then write C vector equal to A vector plus B vector. Don't forget, always think of the symbol plus and equal to in the equation showing vectors addition and combined with and equivalent to. The meaning of these symbols are different from their meanings in ordinary algebra with added to and equal to. We use special methods, namely the triangle law of vector addition and the parallelogram law of vector addition to determine C vector. These are equivalent methods and you have studied them in your school physics. Let us now state these laws. Say figure A. Vector addition, triangle laws. To add two vectors A and B and determine some C vector equal to A vector plus B vector. Draw them in such a way that the head of the first vector say vector is joined with the tail of the second vector say B vector. Draw the arrow from the tail of the first vector A to the head of the second vector B. Represent the resultant vector C vector equal to A vector plus B vector. The triangle law of vector addition for two vectors A and B. A, B. A vector, B vector, A vector, B vector, C vector equal to A vector plus B vector. It is better to use the parallelogram laws of vector addition when the two vectors we want to add have their tails at a common point. For example, this method is useful when we want to find the resultant of two forces acting at the same point on an object. Using this law, we can calculate algebraically the magnitude and direction of the resultant vectors. Parallelogram law of vector addition. The sum C vector equal to A vector plus B vector of vectors A vector and B vector with their tails at a common point O is represented by the diagonal OC of the parallelogram through O with A vector and B vector as its sides. The parallelogram law of vector addition. A vector, B vector, O, alpha, theta, C vector, C. Note to find the sum A plus B of two vector A and B situated at different points, shift the second vector B vector parallel to its so that its tail joins the head of the first vector A. Draw the vector from the tail of the first to the head of the second. Note that the vector sum C vector lies in the plane containing vectors A and B, which is the plane of the page you are reading. You can think of adding two vectors, A vectors and B vectors, taking two successive walks. Their vector sum is the vector from the beginning point to the end point. Note that here we are using the concept of equality of vectors. You may like to know what are the magnitude and direction of the resultant vectors. The expression for the magnitude and direction of the resultant vector for two vectors A and B having the angle theta between them are given as follows. C equal to root over B square plus 2AB cos theta plus A square. Alpha is equal to tan inverse of A sin theta by B plus A cos theta. Here A, B and C are the magnitudes of the vector A, B and C respectively, and the angle alpha between the vector B and C gives the direction of the vector C. See figure. You can prove equation A and B yourself. This is given in terminal question 8. Note that vector addition is not an algebraic sum. We cannot add the magnitude of the vector A and B to get the magnitude of vector C. The two methods of vector addition described above are called the graphical method, where we use the geometric representation of vector. What happens when you wish to add more than two vectors? Vector addition is binary, which means that just like numbers, you must add vectors 2 at a time before you revise how to do that. You may like to recall two important properties of the sum of vectors. Properties of the sum of vectors. 1. Commutative property of vector addition. The sum of two vectors is the same whatever be the order in which the two vectors are added. You can verify from figure that A plus B equal to B plus A. 2. Associative property of vector addition. If more than two vectors are added, it does not matter how they are grouped. A plus B plus C equal to A plus B plus C. Vector addition is commutative. A vector, B vector, C vector equal to A plus B, A, B, C vector equal to B plus A, C vector equal to A plus B, B, A. You may like to verify the associative property of vector addition before studying further. For this, you will need to apply the triangle law of addition. Twice study figure and then attempt SAQ2 for adding more than two vectors. Vector addition associative D vector equal to A plus B plus C equal to A plus B plus C. A, B, C vector D vector equal to A plus B plus C, A plus B vector, A vector, B vector, C vector, B plus C vector, C vector, B vector, A vector, D vector equal to A plus B plus C. SAQ2 adding more than two vectors. Comment this. A vector, B vector, C vector, D vector, A, B, F1 vector, F2 vector, F3 vector, adding more than two vectors. It may seem from figures 2 that all vectors lie in the same plane, which is the plane of the paper. This may not always to be true. For example, in figure, the vector C may not lie in the plane of the vector A vector plus B. Then the geometric representation of vectors is not convenient. If all the vectors do not lie in the same plane, you will have to draw each step of equation separately. Polygon law of vector addition. While solving SAQ2A, did you note that the resultant is the vector drawn from the trail of the first vector in the sum to the head of the last vector in the sum? This is the polygon law of vector addition with the margin remark. If a number of vectors is represented in magnitude and direction by the sides of a polygon taken in order, then the resultant vector is represented in magnitude and direction by the closing side of the polygon taken in the opposite order. That is, from the tail of the first vector to the head of the last vector. See figure. Polygon law of vector addition applied for determining the resultant a plus b plus c plus d of four vectors a plus b, c and d. A, B, C, D. B, A, B, C, D. A plus B, A plus B plus C, A plus B plus C plus D. You would have noted in your answer to SQ2 that even if we use a different sequence of vector for addition, the end result is the same. Now suppose you wish to add a vector a 3 times to determine a plus a plus a. From vector addition you can see that the sum is a vector with 3 times the magnitude of a, and in the same direction as a we can extend this idea to the product of vector with a scalar m. Let us give a formal definition. Multiplication of a vector by a scalar. A vector a, when multiplied by a scalar quantity m, is equal to the vector ma. It has magnitude mod m mod a also 1 if a not equal to 0 and m greater than 0, then ma is the same direction as a. If a not equal to 0 and m less than 0, then ma is the direction opposite to a. 3. If a not equal to 0 and m equal to 0, or a equal to 0, then ma equal to 0. In physics, there are many quantities which involve the product of a vector with a scalar. For example, the linear momentum p of a particle of mass m moving with a velocity v is p equal to mv. As per Newton's second law of motion, for a particle of constant mass, the force F vector is the product of its mass and acceleration. A vector is to F vector equal to m into a vector. So far, you have learned how to add vectors geometrically. Let us now revise the concept of subtraction of vectors. Multiplying a vector by a scalar, a vector, 2.5 a vector minus 2 a vector. For a scalar m, mod m, and always a positive quantity, mod m equal to m if m greater than 0 and mod m equal to minus m if m less than 0. A plus 0 equal to a plus minus a equal to 0, m of a plus b equal to m into a plus m into b, m plus n of a equal to m into a plus n into a, m of na equal to mn of a, 1a equal to a, 0a equal to 0, minus 1a equal to minus a. Subtraction of vector. To subtract vector b from the vector a of the same type, we add the vectors a and minus b. A minus b equal to a plus minus b. This is also called the difference of two vectors a and b. Recall that the vector minus b is a vector of same magnitude as b but opposite in direction. If you interchange the head and tail of any vector a, you get the vector minus a. Note that unlike vector addition, vector subtraction is not commutative because b vector minus a vector equal to minus a minus b. Thus the vector b minus a and a minus b are equal in magnitude but exactly opposite in direction. We now show you how to subtract vectors. A vector, b vector, a vector, b vector, b, a vector minus b vector, a minus b vector, c, a vector, b vector, a minus b vector, d. A subtraction of vector from vector a Reverse the direction of B to get minus B, add A and minus B, the alternative method. How to subtract vectors? Suppose you have to subtract vector B from vector A shown in figure A. Since A minus B is a vector, A plus minus B, we can reverse the direction of vector B as shown in figure B and then add it to A to get A minus B. Alternately, when A minus B is added to B, it gives A. Hence, we can move B parallel to itself so that the tails of A and B are placed together. Then A and B is the vector from the head of B to the head of A. You may now like to solve a problem on vector addition and subtraction. SAQ 3, addition and subtraction of vectors. Comment this. Products of vectors. Note that unlike vectors addition in the scalar product of vectors, the vectors need not represent the same physical quantity. Vectors can be multiplied in two different ways to give either a scalar or a vector depending on whether the result is a scalar or a vector. The product is called either a scalar product or a vector product. Again, if you know this concept well enough, just try the SAQs given in the section. If you are not able to solve them, go through this section carefully and then try the SAQs. Scalar product. Let us first define the scalar product and state its properties. Scalar product and its properties. The scalar or dot product of any two non-zero vectors, A vectors and B vectors, is written as A into B vectors and is a scalar quantity defined as A vector into B vector equal to mod of A vector of B vector cos theta equal to AB cos theta. The angle theta is the angle between the A and B, or more properly between the direction of A vector and B vector as shown in figure A. When they are placed tail to tail, there are actually two such angles, theta and 360 degree minus theta or 2 pi minus theta. However, either of these can be used as their cosine have the same values. The product A into B is pronounced at a dot B. We now state some properties of scalar product which follows from its definition. If the two vectors are parallel, their scalar product is maximum. A into B equal to AB for theta equal to 0 degree, since cos 0 degree equal to 1. If the two vectors are perpendicular to each vector, we have A into B 0 for theta equal to 90 degree, since cos 90 degree equal to 0. The scalar product of a vector B with itself is given by B dot B is equal to B square, or B equal to root over B into B. The angle between the vectors A and B when these are placed tail to tail is given by cos theta equal to A dot B by AB. Commutative property. Scalar product is commutative as it is a scalar quantity and does not depend on the order in which the vectors appear. A dot B equal to B dot A. Distributive property. Scalar product also obeys the distributive law. A dot B plus C equal to A dot B plus A dot C. A vector theta A dot B vector greater than 0, B vector 2 pi minus theta. B, A vector A dot B vector equal to 0, theta 90 degree. B, A vector B vector C, theta A dot B vector less than 0. Definition of the scalar product: that scalar product of vectors at acute angles is positive. Scalar product of perpendicular vectors is 0. Scalar product of vectors at obtuse angles is negative. There are many scalar quantities in physics that are expressed as the scalar product of vectors. For example, the work W done on an object by a constant force F during its displacement d is the scalar product F and d. W equal to F into d. See figure A. Power P is defined as the rate at which work is done by a force on an object and is expressed as the scalar product of the force F applied on it and its velocity v. P is equal to F dot v. The potential energy U of an electric dipole having dipole moment P placed in an electric field E depends on the angle which the dipole makes with the field. It expressed as the scalar product P and E, that is U equal to P dot E. The potential energy U of a magnitude dipole moment mu vector in a magnetic field V vector depends on the angle between the magnetic dipole and the field U equal to mu dot B, figure C. Examples of scalar product in physics. A. F theta d vector. E theta minus q p vector plus q. B. C theta b vector b. We can use the scalar product to determine the projection of one vector on another vector. The projection of a vector A on another vector B is defined as the component of A along B. It is A vector mod cos theta, where theta is the angle between A and B. Also the component of the vector A in the direction perpendicular to the direction of B is A vector cos 90 degree minus theta or A sin theta. Thus the component of A parallel to B, A dot B by B vector, A mod cos theta. The component of A perpendicular to B equal to A mod sin theta. You may now like to solve an FAQ on the concept of scalar product. B cos theta is the component of vector B along the direction of vector A. A cos theta is the component of vector A along the direction of vector B. B cos theta 90 degree, A vector, B vector, theta, A cos theta. Projection or the component of the vector along the direction of another vector. FAQ 4 scalar products of vectors. Let us now study the vector product. Vector product. In many cases in physics, the product of two vectors is a vectors. We therefore introduce another useful product of vectors called the vector product or cross product and devise special notations for it. Definition of the vector product, right-hand rule for the direction of the vector product. A vector, B vector, C vector equal to A into B, theta, A. B, A vector, B vector, C vector, theta, left to right. Thumbs up. Introducing the vector product. The vector product of the vector A and B is the vector C, A into B given by C equal to A cross B, AB sin C cap, with magnitude C equal to AB sin theta. Here, theta is the angle between A and B, or more properly between the direction of A and B. When they are placed tail to tail, there are actually two such angles, theta and 360 degree minus theta. Since the sense of these angles have different values, we take the smaller of the two angles in the calculation. Thus, 0 less than equal to theta less than equal to pi, figure A. A into B is pronounced as A cross B. The direction of the vector product is given by the unit vector C cap, which is the unit vector perpendicular to the plane containing of the vectors a and b. We determine the sense of c vector from the right hand rule. Curl the finger of your right hand so that your fingertip point in the direction of rotation A towards B. Then the extreme thumb, as shown in figure B, gives the direction of C. Defined in this way, the vector A, B, and C are said to form a right-handed triad. To understand the point about the order of vectors, can you tell what is B into A? Follow the definition of the vector product given above. If you curl your fingers around the line so that your fingertips point in the direction of rotations of B to A, then your thumb points in a direction opposite to that of A into B. Thus, the direction of the vector B into A is opposite to that of the vector A into B, but the magnitude of both vectors are equal. Thus, we have A into B equal to minus B into A. Therefore, the vector product is non-commutative. We also say that the vector product is anti-commutative. Don't forget, the order of the vectors is important. In the vector product is not commutative. We can express many physical quantities as vector product. Here we give some example. Torque. You may have learned in your school courses about torque. When a net external torque is exerted on an object, it brings about a change in its rotational motion. The torque on an object is defined as tau equal to R into F, where F is the net force applied on the project and R is the position vectors of the point of the application of the force from a point on the axis of rotations. Angular momentum. The angular momentum L of the particle with respect to a chosen origin is defined as the vector product of the position vectors of the particle with respect to the origin and its linear momentum L equal to R into P. The force acting on a point charge q moving with a velocity v in a magnetic field is given by F equal to qv into B. The force acting on an element of a current carrying conductor in a magnetic field B is given F equal to IdIB into B. Where I is the current through the conductor, we now state some properties of the vector product. Rotating wheel, position vector, force of friction F, O, V vector, R vector, theta, L vector equal to R into P. Examples of vector products in physics: a torque on the rotating wheel points into the pitch perpendicular to the plane of the paper. B. Angular momentum of a particle having position vector R and linear momentum P vector. Properties of the vector product. The vector product of the two parallel vectors is a null vector. Figure A. Thus, A into B equal to 0. Since theta is 0 and sine 0 degree equal to 0. The vector product of a vector with itself is a null vector A into A equal to 0. From the definition of the vector product, it follows that k of A vector equal to B, k of A into B equal to A into k of B. The vector product of two vectors perpendicular to each other is maximum. Figure B. Thus, A into B, AB n, when theta is 90 degrees, since 90 degree equal to 1. Here n is a unit vector perpendicular to the plane containing both A and B, and its direction is given by the right hand rule. Vector product is anti-commutative. A to B equal to minus B into A. The vector product follows the distributive law, that is A into B plus C equal to A into B plus A into C. The vector product is not associative, that is A cross B cross C, not equal to A cross B cross C. vector products of a parallel and a perpendicular vectors. A vectors, B vectors. A cross B equal to 0. A cross B mod equal to AB, A, B. FAQ 5 vector products. Comment this. The vector product also has a geometrical interpretations, which we now explain through an example. Example 1.1 Geometrical interpretation of the vector product as area vector. Usually you think of area as a scalar quantity, however in many applications in physics, example while calculation flux, we also want to know the orientation of the surface of a given area. For example, suppose we want to calculate the rate of which water stream flows through a while loop of a given area. The rates of flow of water will be different when we place the loop parallel to the stream and when we place it perpendicular to the stream. When the loop is parallel to the stream, no water flows through it and the rate of flow is 0. So let us now see how the vector product is used to specify the direction of an area. Geometrical interpretation of vector product as an area vector. A, B, A, H equal to B sine theta, theta. Consider the area A of the parallelogram with the vectors A and B as its two adjacent sides. Figure. Note that the tails of the two vectors are at the same point and the angle between the vectors is theta. The vector product A cross B has a magnitude of AB sine theta. Perpendicular to the plane containing the vector A and B. From figure, you can see that the area of the parallelogram is given by A equal to A into H equal to A of B sine theta equal to A cross B of mod. We can therefore define the vector representing the area of the parallelogram of adjacent sides A and B as the vector product of these vectors A equal to A cross B. By the definition, the direction of the area vector is perpendicular to the plane of the parallelogram and its sense is given by the right-hand rule. Thus, the area vector A is normal to the surface. Remember, the sense of the area vector is arbitrary, but once we choose it, it is unique. We now summarize concept you have studied in this unit. Summary. Concept. Description. Scalars. The physical quantities that are completely specified by a number followed by an appropriate unit of measurement are scalars. Vectors. The physical quantities that are completely specified by a magnitude which is a non-negative scalar quantity and a direction in space are vectors. A vector is represented geometrically by an arrow, a directed line segment. Equality of vectors. Two free vectors are equal if they have the same magnitude and direction regardless of the position of the tail of the vector. If a vector B has the same magnitude but the opposite direction as any other vector A, then we can write B equal to minus A. Unit vector. A vector of length or magnitude 1 is called a unit vector. By convention, which unit vector are taken to be dimensionless. A unit vector is used to denote a direction in space. Any vector A can be represented as the product of its magnitude A and a unit vector along its direction denoted by A. Then we have A vector equal to A into A cap, or A cap equal to A vector by A equal to A vector by mod of A vector. Addition and subtraction of vector. Triangle law of vector addition. If two vectors A and B to be added or represented in magnitude and direction by the two sides of a triangle taken in order, which means that the tail of B is at the head of the vector A, then their sum of resultant is given in magnitude and direction by the third side of the triangle taken in the opposite order. That is from the tail of the first vector to the head of the second vector. Figure. Parallelogram, law of vector addition. If the two vectors to be added are represented in magnitude and direction by the adjacent sides of the parallelogram, then their resultant is given in magnitude and direction by the diagonal of the parallelogram drawn through the point of intersection of the two given vectors. Polygon law of vector addition. If a number of vectors are represented in magnitude and direction by the sides of a polygon taken in order, then the resultant vectors are represented in magnitude and direction by the closing sides of the polygon taken in the opposite order. That is, from the tail of the first vector to the head of the last vector. Vector addition is commutative and associative. A plus B equal to B plus A and A plus B plus C equal to A plus B plus C. Subtraction of a vector B from a vector A denoted by A minus B is just the sum of the vector A and minus B. A minus B equal to A plus minus B. Multiplication of a vector by a scalar. A vector A when multiplied by a scalar quantity M is equal to the vector Ma having the magnitude Ma. The following is true for the multiplication of a vector by a scalar. Mn of a vector equal to mn a vector equal to mn a vector, associative law. M plus n a vector equal to ma plus na and m of a plus b equal to ma plus mb, distributive laws. If m equal to 0, then ma is null or 0 vector which has 0 magnitude but no definite direction. Scalar product. The scalar product of two vectors a and b called a dot b and denoted by a dot b, the scalar quantity defined as a dot b equal to mod of a into mod of b cos theta, ab cos theta. Components of a vector in a given direction. A vector can be resolved into its component vector along any arbitrary direction. The components of a vector A parallel and perpendicular to any other vector B which makes an angle theta with a vector A are given as the component of A parallel to B minus A dot B by mod of B equal to A mod cos theta. The component of A perpendicular to B mod of A sin theta. Vector product. The vector product of two vector A and B called A cross B and denoted by A cross B is a vector quantity defined as C equal to A cross B, AB sin theta C cap with magnitude C, AB sin theta. The direction of the vector product is given by the unit vector C cap, which is a unit vector perpendicular to the plane containing the vector A. We determine the sense of C cap from the right hand rule. Terminal questions. Forces on an object. F1, F2, 120 degree, 120 degree, W. Diagram of TQ12. A, B, C, D, E, F. F1, F2, F3, F4, F5. Diagram of TQ13. X, Y, A, B, 45 degree, north and east. Diagram for TQ14, 45 degree. Comment this. Solution and answer.